Okay. Okay. I'm happy to introduce you to Pallav Sarma. He is with Tachyus, and my first interaction with them was Tachyus. That sounds like a great name for a computer. And I guess I met you 10 or 12 years ago, and we've kept in touch on and off. I didn't realize at the time that he'd worked for Chevron and for Schlumberger, but he's the technical officer and one of the founders of the company. And most of them moved to Houston, and like most of us, he did not go. But he still works for them with the wonders of the computers. So with all the interest that's been shooting around and some of us coughing and sputtering about AI, I thought he'd be a perfect one to introduce us to some of the ins and outs of what works and what maybe hasn't worked. And to give you a short biography on him, he's the co-founder and chief technology officer for Tachyus, responsible for the modeling and optimization technologies underlying the Tachyus platform. And he'll go through an example for us, and he will answer questions. He's a renowned expert, closed loop reservoir management, going through the whole cycle, setting it up, and then monitoring reservoirs as they continue and trying to optimize production and any work that needs to be done on them. He has many years of research experience in the oil and gas industry, working for Chevron and Schlumberger prior to Tachyus. He has received many awards from SPE, international organizations. He was Chevron's Excellence in Reservoir Management Award, and he's got 2 PhDs, or one in petroleum engineering and one, excuse me, I must have caught what you had, through Stanford, PhD in operations research. So he's worked on all aspects of the, as we call it, downstream part of the oil industry. But as you will find out as you're going through this, and we've talked about water and reservoirs, whether they're fluid, gas, or whatever. And so they've been working on all types of reservoirs, and applications are going to increase with time. And one of the beauties of it is everything can be done a lot faster. Now, the concern I always had is faster, but is it better? And the complaint I had with the reservoir modelers was you'd put a lot into getting the information for a reservoir model, you'd put it together, and then every 5 years you'd say, well, how's it going? I don't know. So there was no way to really do a rapid update as you were drilling wells, put the data in, see what's responding, see how it's working, see if you need to change your objectives, or if it's not working, was something wrong with the assumptions in the model. So I thought that would be very interesting for us, but I know we also have people in hydrology, and as we're looking at sources of methane, et cetera, and how to handle CO2, this type of work will be used more and more. So with that, I will introduce our speaker today, Pallav Sarma. Thank you for coming tonight.
That'll definitely make it easier. Hopefully this starts working. No. Okay, no worries. Well, thank you very much, and thanks, Paul, for the invite. Yeah, so it's great to see quite a few Chevron faces here. So I didn't realize there were so many Chevron people here. So yeah, I live again in Danville, 20 minutes away. So it was a great opportunity to come here and talk about the things that we're doing. So my talk today, and again, maybe I'll give you a little bit more about Tachyus before I start. So yeah, we were founded in 2014. The idea was to apply data science and machine learning in the oil and gas space, and also to avoid going to Houston. So this is where Chevron was moving everyone. So that, hey, how do I stay here? So okay, let's start. So anyway, jokes aside, so the idea was that, yeah, it seemed like oil and gas industry was a little bit backward in the applications of machine learning. So this was an opportunity to see how we can sort of leverage some of these techniques to sort of improve some of the operational decision making and other things that you can do with this kind of modeling. So yeah, so my talk today is about combining reservoir physics and machine learning into this new modeling paradigm that we call data physics. And so the idea is to combine these disparate modeling worlds, right? One that of traditional reservoir modeling and simulation, and the other of data science and analytics. So these two disciplines have traditionally been quite different, like different people doing these disciplines. The technologies are also quite different, but there's a lot, I think, there's possibilities of combining them together to sort of get the benefit of both worlds. And that's the general idea of how we can do that. Okay, so before I begin my talk on this particular subject, so one question, are the questions in the end, or is it like you guys can ask questions whenever? How does it work here? Okay. Well, yeah, if you have time, then I'm happy to answer whenever. I mean, yeah, it's an informal talk, I'm assuming so. Yeah, so before I talk about this particular subject, I wanted to sort of kind of give you an idea about the relationship between machine learning and digital transformation. So digital transformation is one of the key initiatives that I think has been undertaken in the oil and gas industry for at least last 30 years. And if you look at this, so this is the analysis by McKinsey, which says that a digital transformation will have a big impact on reservoir modeling and production optimization and process automation, right? So that the dark blue color has been basically a high impact, I guess, right? So, and if you look at the next slide, so this is one of many articles that says that AI and machine learning are key enablers of digital transformation, right? So that is why I think it is easy to understand why nowadays AI and machine learning has become an important part of the toolkit for reservoir modeling, production optimization, and operational automation. So that's kind of the background of where we're trying to go with respect to this. And that's kind of also the thesis of our company. So if you look at what we're doing, it's basically digital transformation for energy and sustainability. So that's how this kind of fits in towards our mission. Okay, so with that, I'll start with the agenda of my talk. So I'll talk about what's called closed loop optimization, which is basically a way to do continuous model-based optimization of operational decisions, right? That's the general idea. And in fact, closed loop optimization is also a topic of interest in the oil and gas industry for at least the last 30 years, because it's a precursor to digital transformation. So, I mean, if you guys in Chevron would know that we used to call smart fields, right? That was a big thing when we were there in 2000, around early 2000s, right? And then Shell used to call it something similar. BP had field of the future or something like that. So all those are kind of the precursors to digital transformation, that the general term that we use today. So there are three main components to this closed loop optimization. So one is what we need is a fast and reliable forward model. Again, if you guys are, I think if you're in geology and in reservoir engineering, people, you understand simulation, reservoir simulation, and the modeling behind it. So that's kind of the general idea. People use simulation as is one kind of forward model. In our case, it will be a different kind of forward model, and I'll talk about why that is needed. Then you also need efficient ways to assimilate data into models. And that's basically that's the idea. As Paul just said, hey, you have a model that's 5 years old because it's just very difficult to update your model. So how do you update models more efficiently? And that's the idea behind these kind of real-time data assimilation algorithms. And then, of course, you need efficient ways to optimize these. So if you have a model, you want to optimize operational decisions, right? In the case of oil fields, you're optimizing locations of wells, injection rates, all kinds of operational decisions. So how do you do it in a quantitative way and an efficient way? You need algorithms that allow you to do that efficiently. And that's what this is about. So I'll go into a little bit of detail about these two topics, but most of the talk will be focused on the modeling part here, because that's kind of the key differentiator of the key new things that we're trying to do today. So then with respect to applications, so I'll talk about two applications. One is a water flood optimization case study. And this is about optimizing injection rates in a water flood to maximize different kinds or minimize different kinds of objectives, like maximizing production, minimizing cost or injection. It could be anything that you want to optimize to set up the problem properly. So then I'll talk in this particular application, I'll talk about how we assimilate data into these models, how we understand that the model is predictive, and then talk about the actual optimization problem, which is redistribution of the water, and then also optimizing total injection capacity. And then I'll show actual field implementation and results. So this is a project that has been going on since 2019. So it's a field in Argentina operated by a joint venture between BP and a local operator there. So this is a real case where we have implemented the results from these models, and we have monitored the results and saw how it's working, what's not working. So that's kind of, I think, interesting to see. And then another application here of the same technology is infill drilling optimization. So using the same kind of models, but changing the optimization problem. Now you want to optimize the location of the wells, the number of wells that you're going to drill. That's going to optimize, maximize net present value while minimizing drilling cost. Right? And then I'll talk, give a summary of the talk. So feel free to ask questions at any time, because there's a lot of stuff here. So I think it's if you want, and we can stop and discuss on a particular topic. So closed loop optimization, and again, Wayne might have seen this slide since my days in Chevron. So in fact, this was the topic of my PhD at Stanford. And then, of course, things have evolved over that time. I think, as I said, this has evolved a lot during that time. Of course, the underlying algorithms have evolved over time to make these things more efficient, but the general idea has been there for quite some time. So again, to kind of give a high-level overview, so the basic idea of closed-loop optimization is that we have a real reservoir, real oil field, any physical system, basically, really, right? So the idea is that you have some data that is coming out of the system, like measurements and from sensors or whatever else, and then you have some sort of a centralized repository where you get data, and then use the data to, and then you have these models, one or more models that represent your system. As I said, this could be all kinds of models. It could be a traditional simulation model. It could be a pure machine learning model. It could be analytical models. It could be these data physics models that I'm talking about. So now, as I said, so this is something that Chevron has been working on for quite some time, and not only Chevron, others have been also. But one of the key issues is that in Chevron, we're using simulation models as this underlying model, right? So the problem with that is that simulation models are extremely expensive to build and run. I mean, you guys are familiar, some of you are familiar with that, right? It takes months to build a good model, sometimes years to get the models calibrated to data, and it takes hours to days to run it a single time, right? So if it takes hours to run a single evaluation of the model, optimization requires running these models thousands of times, sometimes hundreds of thousands of times. So it becomes very difficult to use these models practically. So this closed loop optimization is not practical when you have models that take a long time to run. So that's where this kind of approaches come in, like models that are fast enough that you can actually do this kind of loops in a practical amount of time. So now going back to the loops, so these models are representations of the real field. Then as you get new data, you update your models with the latest data in order to minimize uncertainty of this model. So again, as Paul was saying, you need to update your models, right? Otherwise, your models become stale because the models are uncertain. We all know that our models are wrong. So as you get new data, you have to update them, right, to minimize the uncertainty. So that's what the data assimilation does. So as you get new data, you'll update your models. Generally, at least semi-automatically, you want this process to be fast enough so that you can actually make this loop work in practically. So once you do that, then once you updated your models, and then you go to the next step, which is optimization. And in this case, as I said earlier, we are doing what's called multi-objective optimization. So you're not only looking at one objective, you usually look at more than one, like net present value, cumulative oil production, cost. In nowadays, people are interested in reducing emissions. So that could be another objective. How do you produce more while, for example, minimizing carbon intensity? Because that has become an important problem for people. So you generally have all these different objectives that basically you want to optimize over, and you have a set of control variables that you are changing in order to make this optimization. So in the example that I'm going to show, that the control variables are the injection rates, right? So you have, let's say, 100 injectors. You have some amount of water that you can inject. So you have to decide how much water you're going to inject in each well over time, and it's going to change over time. So if you are running this field, let's say for 10 years, and you're going to change injection rates, say, every month, then it becomes a very large number of optimization variables, right? So that makes it a very complex optimization problem. So that's why you need efficient ways to sort of make this solve this optimization problem. And you also need to be able to scale this on cloud computing, because otherwise it becomes very difficult to solve it. So not only do you need fast models, you need fast, efficient optimization algorithms, and also you need a lot of computing power. And that's what the cloud computing allows us to do today. So you can scale up these optimization problems to thousands of cores, run the optimization, then of course, then shut them down when you don't need them. So that's the general idea. So once you've done that optimization and you find the optimal values of your control variables, then you go and apply them on the real field. So you go and make the changes in the real field, then you get new data from the field, and then you go through the process again. So that's why it's a continuous closed loop process, right? So that's the general idea behind closed loop optimization. So now, as I said earlier, so the main difference of what we are trying to do today is to make this practical. And the way to do that is creating these models that are efficient and can be run fast, while at the same time, they have good predictive quality. And that's the main topic of my discussion. How do we get models that are fast enough, but at the same time are generally robust? So if you guys are a little bit familiar with, like, I mean, I'm sure a lot of you are familiar with traditional modeling, and maybe some of you are also familiar with machine learning. So this is, I think, slide tries to give you an idea of how these are similar or different, and how we leverage them to create this new kind of techniques, right? So if you think about traditional modeling or simulation, the basic idea is that you have some X, let's say, which is your input, like your control variables, let's say injection rates. And then you have a set of rules F. In the case of like traditional simulation, these rules are your physical equations, your conservation of mass, conservation of energy, Darcy's law. All these are the equations that govern your system, right? So F is basically those equations or set of rules. So what is the output that we're interested in? Let's say oil production. It could be any other thing, right? So a traditional forward model is a forward model in the sense that you have X, you apply F on it, and then you get Y, right? So that's what a traditional simulator does. You can kind of do it every time step. You basically have injection rates, then every time step, the injection rates might change, and you apply the rules, and that gives you the pressures and saturations and all those things that allows you to calculate your oil production, right? So Y equal to F of X in a very general way and simplified way of saying that, but that's what basically a traditional simulator is. Now, machine learning is kind of the opposite, right? So where the idea here is that you are given some historical inputs and outputs. So XO is your historical injection rate. So let's say you have this oil field that you've been running for 10 years. So you have your historical injection rates of those 10 years. You also have your historical oil production, YO, in this case, Y observed. So the idea of machine learning is now that you are saying that, okay, you do not know the relationship between X and Y. You want to find the best relationship that basically between X and Y through solving this minimization problem. So what you do is that Y0 is your observed output, that you know, and you want to find, as I said, the relationship or nonlinear, usually a nonlinear mapping between Y, X, and Y. But basically what you're saying that I want to find F. If I apply F on X0, it gives me Y calculated. So I want to find F that minimizes the difference between Y and Y observed. And F is basically belongs to this universe of functions, capital F here, which basically is a set of all kinds of possible mappings. And in general, yeah, go ahead, please. Yeah. Yes. So in machine learning, you are saying that you don't know the function. And you're saying, okay, I know the data, I know the historical data. I want to find the best function that matches my historical data, right? So, and that's what you're trying to do. You don't, and what you do is, in general, you're trying to find this function from a universe of functions. And there are well-known functions like neural networks, support vector machines, and all these are very general, well-known functions that are out there that you can apply and basically try to solve this minimization problem. So once we have minimized that, like, and you're satisfied with that minimization, then you'll come up with a function form that this is, okay, this neural network or this support vector machine matches my data, and therefore it's a good model to go forward with, right? So now both approaches have pros and cons, right? In the first, the benefit is that at least for problems like water flooding or most of the reservoir engineering problems, the physics is very well known, right? And understood for 50 years or more, and people understand and trust them. And if you can build a good simulated model, like it may take time, But if you can build a good model, you can trust it, which basically means that you can use it for long-term predictions. You can predict the next 5 years, 10 years, and you can generally rely on it because people use it, for example, to book reserves, right? Things like that you can do with these models because the physics is understood and well-known and trusted. But the problem, as I said, is time. It is just too time-consuming to build these models. It takes a long time to run these models. And if you have to run this model 100,000 times, it's just impossible to sort of do this kind of optimizations that we want to do. On the other hand, machine learning, again, is the opposite. It's basically very easy to, very fast to build models. So once you have the data, like building a traditional machine learning model, like a neural network, usually takes a few days for expert data scientists, right? And it's also very fast to run them. This takes like seconds to run. So you can run this millions of times in a matter of minutes, right? But the problem is that these models are not that reliable. And that's one of the reasons why it has not become as popular as it could have been in the oil and gas industry, because machine learning is not new. I mean, the oil and gas industry, in fact, neural networks have been known at least 40 years. So it's not, the technology itself is not new, but the problem is that due to the scarcity of data, I mean, in oil and gas, we know that we don't have a lot of data, not like, for example, Facebook and Google, they have trillions of data points. We don't have that kind of data. The other problem is noise in the data. As we know, I guess a lot of you know, the data that we're collecting is extremely poor quality. There's a lot of noise, a lot of errors in the data, and that makes it very difficult to build good quality machine learning models. And the other big problem with machine learning is that these models will not guarantee to honor physics. So, and you know that in if a system is driven or governed by physics, you want to make sure that certain relationships are always honored, right? If you come up with an answer that doesn't make any physical sense, it's very hard to gain trust in a model like that. I mean, if you're a reservoir engineer or geophysicist and you see a result that makes no sense, then even though it might match your historical data, you still cannot use it, or you still cannot use it for forward predictions because you just don't trust the model because it doesn't make physical sense. So the question is then, how do we build models that kind of get the benefit of both worlds, right? Models that are fast, that can be built quickly, that can run quickly, but at the same time have long-term predictive capacity and also honors physics. And that's the idea behind this data physics approaches that I'm talking about. So any questions, any more questions on that? Because this was an important slide. Yeah. Exactly. Yeah. I mean, yeah, this is again for the sake of simplicity of explanation, but y and x are both vectors basically. And yeah, and basically they can be. Yeah. So down to look, what is this idea behind data physics, right? So if you saw this part, this is the same as the machine learning part you just saw, right? So what we are trying to do is we are trying to find this f functional form f that minimizes the difference between your observed output and your calculated output y by the application of f, right? So what we are saying now is that we of course want to minimize that because of course we want to match historical data, but we also want to find a model that's f that also matches or minimizes the difference between it and my known physics. So G basically stands for all my known physics, right? In the case of water flood, it's like the mass balance equations, the Darcy's law, PVT models, rock fluid models, all these basic equations that define a water flood. So the idea here is that we're saying we not only want to find F that minimizes my difference between my calculated historical observations, I also want to find F that minimizes itself from the known physics, right? And lambda P and lambda D are the weights of these two terms. So if lambda P is 0, this goes back to traditional machine learning, so there's no physics in it. And if lambda D is 0, then the best approximation of G is F, so G is G itself. So basically this will turn out to be a traditional simulator, right? So the idea here is that you're trying to balance that difference between physics and your data, right? You're trying to find that balance, kind of in models that matches your physical information or physical equations, and also your underlying historical data. So the benefit of this, as I said, is it is still a machine learning model, so you can actually build it very quickly in a matter of days to weeks. And in general, what we've seen through our experience is that it takes us about a month or so to kind of build a good model and go through the entire exercise of, after you get the data and data cleaned up and everything, it takes us about a month to build a good model. And then running these models takes like a few minutes. So, and when you can scale on cloud computing, then you're able to run thousands of these in a matter of hours, and then you can actually do the kind of optimizations that we want to do. And the other aspect is, of course, that by adding the physics term, you are guaranteeing that you are going to have solutions that are physically realistic and physically robust. So they will honor your physical equations, and therefore, if the answers that you're going to get out of this will make sense to if you show it to a reservoir engineer or petroleum engineer, right? So that's a general idea behind what we're trying to do. So in general, these techniques are known as physics-informed neural networks. So if you search up on Google for physics-informed neural networks, you'll find a lot of papers nowadays, today. I mean, this is something quite not that recent, about the last 15 years or so, these techniques have become popular. Not so much in the oil and gas industry yet, but in other industries, these techniques are becoming popular. And so, and again, because of these kind of benefits, that you get fast models, but that are also robust in terms of predictive capacity.
Lambda D tend to be about half and half, or they.
That's a very good question. So the weights of these weights, generally, I mean, you can take out one weight and you can just have one weight just for the sake of simplicity, right? So this weight of the data term depends a lot on the noise in the data. So the more noisy the data is, lesser the weight will be. And if you look at Bayesian inversion theory, it is basically the inverse of the covariance matrix, if you think about it. Like, so if the bigger the variance of the data, the lower the weight, and therefore more weight the physics will get more weight. So you're saying that I don't trust my data as much, so let the physics have more weight. But if you have a lot of data and really good quality data, then this will be larger, and then you don't need the physics as much because the data has enough information to build a good model. Yeah, that's a good question. I mean, one way to think about that could be that when you build these models, and because one of the things I'll explain later is you can also build these models in a probabilistic manner so that you don't have one deterministic model, you have an ensemble of models, right? And that can be used to predict an uncertain in an uncertain way. So you can get a distribution. Let's say you're looking at oil production. So you can get a P10, P50, P90 estimate of oil production, right? Instead of just having one number. Now you can look at that range and say, and that range depends a lot on the noise in the data, right? So you could say, if you see that range is too big to make a decision, you might say, okay, because if you're looking at making some sort of economic decision, right? And then you look at the P10, and the P10 gives you a negative, let's say the economics becomes negative, right? And the P90 is positive. Now it's very hard to make a decision in this case because you don't know if the outcome turns out to be P10, then you are going to lose money. But if it's P90, of course, you're going to make money. So the problem is then you cannot make a decision in this case. So then what do? You want to reduce, or you want to collect more data or reduce the noise in the data. So that's one way you can think about the problem. If the uncertainty band is too high, that you cannot make a decision, well-informed decision, then it might say that, okay, I need to collect more data, or I need to do something to improve the quality of the data, right? That's one way to think about this problem, I think. Yeah.
So just give us like a very brief
So I see a lot of work in like computational fluid dynamics, like where people use computational fluid dynamics models, for example, in aeronautics, like in the design of planes. Like that's also similar. Very expensive finite element models are used to sort of do the computation, do the design of planes. So there also you can use these kind of techniques to sort of speed up the process. And yeah, I don't have exact like examples I can get back to you, but I have seen, yeah, in general, like problems where like these kind of highly complex computational problems, like where are defined by physical systems, basically, is where you'll see applications. Okay.
So.
Yeah. Yeah, I'm assuming, yeah, again, I'm not too familiar on the petrophysical side, but yeah, if you have physical equations that can be a result of that relate somehow to the measurements, right? So you could make theoretically I mean, if you're thinking about like predictive modeling, I know that people do like measurement while drilling and stuff like that, where in some sense you might want to predict ahead, like ahead of the drill bit, what my properties are going to be. In situations like that, you could use these kind of models because these kind of models will have some physics in it. It's not purely based on the data, but as you are drilling and you're getting data, you're kind of updating those models as well continuously so that you can predict ahead of the drill bit and then sort of make decisions better, I guess, like how to drill. I mean, yeah. And applications, as any application where there's some physical component involved, some physics involved, and where you want fast models, and it is also a lot of data, I mean, this can be applied. Okay, so now with respect to the actual, like the workflow, how this works. So, I mean, it's very similar to traditional machine learning. So there are kind of 3 steps. One, which is called the training of the models, and then validation of the models that, okay, you have a good model. Then, of course, once you've done that, then you go to the optimization step. So as I said, this usually takes us in nowadays, depending on the size of the field, it takes like few weeks to like 1 or 2 months at the maximum. And again, the idea is that you have the underlying equations, then you have the data, then you have the machine learning models to put everything together and come up with the final model. And then once you have the final model, as I said, validation, there are all kinds of validation. One of the basic techniques of validation is what's called back testing, where you basically, if you have, let's say, 10 years of data, you'll use maybe, say, 6 years to train the model. Then you'll have 4 years to predict, and then you compare the results of your prediction versus the real data, and that tells you how good the model that is. There are many other ways to sort of do this kind of validations. I'll show you some of that. And then once you have validated the model, then we'll go to the, which I said is this multi-objective optimization problem, where you're trying to find the optimal values of your control variables. And as I said, the control variables could be injection rates, could be locations of wells, could be whatever problem you're solving. It depends on what you have control on. What are the things that you can change to maximize or minimize your objective functions, right? And the objective functions are again defined by this Pareto front, or this is what's called the optimization problem. And this, as I said, when you scale to cloud computing, you can solve this in a matter of hours. So that's what makes this practical. So you are able to do, once this is set up, the first models are set up, then you can do these optimizations very regularly, depending upon the time scale of the problem. In the case of water floods, I mean, you could theoretically, you don't want to optimize every day. It doesn't make any sense because the problems are, the water flood process is not such a fast process, but you would probably optimize it every, let's say, quarter or so. That's what we usually see people doing. But again, depending on the problem, the frequency of optimization will be different. So, okay, so multi-objective optimization, right? Again, this is an important subject because this is, again, the ultimate objective of doing all of this is getting to what is called this Pareto front of optimal scenarios. So again, I'm not sure how many of you are familiar with multi-objective optimization, so I'll just go quickly over this. So the basic idea, as I said earlier, is that you have more than one objective that you want to optimize. And a lot of the times, these may be conflicting objectives, right? On one hand, you want to maximize production. On the other hand, you want to say minimize carbon intensity, or you want to minimize your water injection, right? Because there is cost associated with it. And a lot of times these are conflicting. So how do you find operating scenarios that are basically best with respect to all these different conflicting objectives, right? That's the idea behind multi-objective optimization. So in this case, I'm looking at 2 objectives. So it's basically a bi-objective optimization problem. So on one hand, I have incremental oil production that I want to maximize. And the other hand, I have incremental injection that I want to minimize, right? So I'll ideally I want to find spend the least and obviously make the most money, right? So 0-0 is here is basically the base case or the do nothing case. So if you have a field that you're operating in a certain way, this is basically the do nothing case. You keep on injecting the same way for the next 10 years, let's say, and that will be your base case, right? So then these points here, the green and blue points are what's called Pareto optimal points. And each of this point is basically an operational plan or injection. In this case, when I'm talking about the water flood, in this case, a specifically injection scenario. So each dot is basically a vector of injection rates. Each one of them is a specific injection rate for every injector and every time step, right? Every time that you're optimizing. So, so this is like that entire operational plan for a field, right? So each of these dots is an entire operational plan. So now if I look at this particular dot here, so this dot is basically the operational plan, which is going to give you the same amount, sorry, it's basically the same amount of total injection, because you can see this is total injection capacity. So you're basically injecting the same amount as the base case, but you're increasing production by about 20%, right? So the idea how you're doing it by redistributing the water. So you're basically finding out where do I put water where it is more effective, and taking the water from areas that are not effective. And then that way you are increasing production basically by increasing your sweep efficiency, right? So that's what's happening with this particular plan. Now, if you look at this other plan here, so this plan is basically the opposite, where you are basically cutting injection by almost 40%, but keeping the same amount of oil production as the base case, right? So if your interest was, hey, I care about my cost, I don't want to produce more, or I might be already producing my target, so I don't need any more production. So you say, okay, how do I then cut my cost to keep the same amount of production, right? So that is that case. So now all of these other points are also called Pareto optimal, in the sense that there are no better plans than these plans when you look at these two objectives, right? For instance, if I look at this particular plan, so you'll see that at this particular amount of injection, there are no other points here on this side, which basically means that for that amount of injection, this is the maximum oil production I can have. This is the best plan in that sense. All these gray dots are non-optimal scenarios. Basically, these are scenarios, there are scenarios like these ones that are always better than these, right? So if you were to choose one, you'll never choose these scenarios. You're always going to choose something from this, right? You could say that, okay, I want to choose a plan that gives me some increase in production and also cuts costs by some amount. So I would choose this plan, right? Instead of choosing this plan or this plan, I choose a plan like this, which kind of cuts some costs and also increases some production, if that's what I want. Or you could also, this could also be dependent on other objectives, because I'm only looking at two objectives here. There could be a third objective or a fourth objective. So that becomes very complex. And it's very hard to see that in, visualize that in, because we can only visualize in 2 or 3D, but sometimes you're looking at more than that. So it's hard to visualize that. But the idea is that basically looking at these multiple objectives and coming up with plans that are basically optimal against all of them. Okay. I think that was all about the general idea. So I didn't, of course, talk about the actual algorithms here because of limited time. But yeah, and if you guys are interested, then I can send papers and stuff to Paul, and then he can, of course, show you. I mean, you can share with you guys. So now, with respect to the example, so this is, as I said, the first case study here, and this is a water flood optimization, which basically means that I am going to optimize the injection rates of my injectors. And as I said earlier, the objective is to show you how we build a good model, that how we build it. So it's a good quality model, it's predictive. And then I'll talk about the actual optimization problem. So yeah, this work was published in SPE. So it was in the ADIPEC in Abu Dhabi in 2021. So this paper was co-written by our client, which was Pan American Energy, which is a joint venture between BP and a local company in Argentina. The field is a very complex onshore field model. It's been in production for over more than 20 years. It's a very complex fluvial depositional environment with over 80 reservoirs. And it was so complex that the operator couldn't build a simulation model because it's just too complex. It didn't have enough understanding of the geology to be able to build a good model. So that's why they thought it was a good case study for something like us, because we are kind of building the model from historical data, right? We are saying that, hey, we're going to build a model from historical data, and basically with the understanding that there's enough historical data that the geological relationship between the wells is captured in that data. And that's the general idea here. Now, of course, I know a lot of you are geologists here, so it'll be good to get your feedback on this, but that's kind of the idea here. So because these are mature fields, there's a lot of data here. How do I use that data and come up with models in a faster way that is maybe sufficient to solve the optimization problem, right? Again, this is not like a panacea for everything. I mean, these are designed for certain kind of problems. A model that I built for water flow optimization may not be the right model for other kinds of things, right? So these are models built for specific purposes, right? What we used to in Chevron is called fit for purpose, right? The idea is that we'll build models that are good enough to solve a particular problem, but it might not be good enough for other problems, right? So anyway, so the idea here is to build a model for this complex system. And it is actually quite a large field, about 100,000 barrels in production. But I mean, for the purpose of this case study, they gave us a fall block that is like constrained, like closed fall block, so that they can study it well. And for that particular fall block, production was about 4,000 barrels and injection was about 70,000 barrels. A lot of injection, like a lot of water cut is very high. But even for this small fall block, there were over 400 plus producer completions and 120 plus injector completions, right? And we're going to optimize all these 120 injector completions because they want to optimize injection at the mandrel level. So they have about 12 mandrels in each injector, and they want to go change injection rates at each mandrel. So you can understand so that how many, and they want to change it every few months. So it becomes a very large number of optimization variables that you want to optimize, right? And then for the purpose of this exercise, we are going to use the last 15 years of data. So we are going to use 9 years to kind of train the model, and then 6 years to do that backtest or prediction. And the data that we're using is mostly production engineering related data, like production rates, injection rates, wells, location of the wells with respect to reservoirs, fault blocks, reservoir pressures, bottom hole pressures, all kinds of data that usually go into a simulation model, except the direct geological data. I mean, we do use properties like porosity, permeability, all those things go into the models because the physical equations are a part of it. But we are kind of reverse engineering that, in the sense that we are saying that what should this properties be in order to match my historical data, right? So directly starting with the inverse modeling problem. Okay, so this is what that back test looks like. So this is that 15 years of data that we are building the model on. This is oil production for that fault block, the block that we're modeling. And then this is the gross production, oil plus water. So this red part is the 9 years of model training. And this blue part is the prediction part, right? And the black dots is the true data, the true production for that fault block. So each of these dot, if you remember, I said that we are trying to build probabilistic models. So each of these dot is basically one ensemble member or one model. So we start off with an ensemble of about 100 models here. And in the beginning, you can see that these dots don't match the data very well. They're all over the place. We're using a technique called the ensemble Kalman filter, which is also a technique that's become very popular nowadays in the oil and gas industry in the last 20 years. And that's the data assimilation technique that we're using. And these are what's called sequential methods. So what you do is initially you start with, it's basically what's called a predictor corrector approach. So you basically start with, how do I go back? So basically it's what's called a predictor corrector approach. So you start with your initial set of models is generally randomized, so they don't match the data. Then you run it forward one time step, you get the true data, and you change model properties to match the data, and it kind of starts converging. So what you'll see here, that initially the models don't match, but over time, as you start assimilating more and more data, the band converges, right? And you can see that the band has become stable after some time. And the side of this band depends on the noise of the data. And this is the question that I think you're asking, hey, how do I sort of understand that? Do I need better data? So this band will be narrower if the data quality is good. If the data quality is not good, this band is going to be wider. But that's the definition of the problem. So then in this case, this is where the band has converged. And then each of this blue line is a prediction from these converged models, right? So you will see that the dark blue line is the mean of all those models. And you'll see that the dark blue line matches the true data very well. Like this is prediction, right? What we're doing in this prediction part is that we're giving the trained models the actual injection rates for this part. What's going on? It's starting working. Oh yeah, seems to be working now. Finally, it's working. Okay, great. Okay, so yeah, so basically what basically happening here is that you'll see that the true data is very well matched by the mean of the models, that mean prediction of the models. And as I said, the prediction is created by inputting into the trained models the actual injection rates, the actual up times, actual bottom hole pressures, and the model is predicting oil production, water production, and gas production. And then you're comparing that to the true data, right? So first of all, you see two things. One, that it matches the data very well in the beginning, but over time it starts diverging, right? You see that the model starts over predicting true data here towards the end, which is expected, because as you start going away and more away in time, it becomes harder and harder to predict. And then that's why you have to do the closed loop. This is not a closed loop. This is a direct full long-term test, but in reality, you'll be updating the models continuously. So this problem should not happen, right? So the other interesting thing to see is this, right? So this, the true data lies within the band of uncertainty. And this is something you also want. So as I said, you are going to predict a P10, P50, P90. So your band should basically, your true data should always lie in this band of uncertainty. Otherwise, your band is too narrow, right? So that's the other thing you want to see. The third interesting thing you want to see is this, right? This is one of the key reasons why these kind of models are good. You'll see that there's this light gray line here. That light gray line is the active producer count. So what you'll see is that in the training part, right, this 9 years, the active producer count was about 250 at this point, right, at the end of the training. But then towards the end of this like period, like 15 years, the active producer count has gone to 450. So total of about 200 new producers were drilled during this prediction part, which had no data during the training part, right? There is no historical data for those 200 producers, right? But yet the model is still able to predict quite well, as you can see from this, like total behavior of the system, right? And that is because physics is a part of this problem. So that is one of the key difficulties using traditional machine learning. Because traditional machine learning models, it is very difficult to predict the behavior of new wells because there's no historical data. When you add the physics into this model, then you're able to understand the behavior, interwell behavior better. As a result, you're able to predict better the behavior of new wells. And as a result, you can get this kind of good quality results. You can see the same thing also here in gross production. It's in fact doing even better than oil. And in this case, because gross production generally has lower errors, because oil, in this case, so it's a 90% water cut. So you have a lot more water production. It's easier to measure. So it's basically therefore you'll get better quality results in the case of water in this case. I mean, again, it depends on the problem, but you'll sometimes see this. Okay, so then, so that was like field level, like predictions, right? Yeah. Yes. No. Yeah. So that's a good question. So first of all, this is not looking at the wells independently. The model is, it's a coupled full field model that we're building. Think of it, it's like a simulation model that you're building. So the wells are related by the physics, right? So if you inject here, how that water is going to go to the nearby producers is governed by the physics, and it's governed by the geology, right? So the premise here, though, is what I'm saying is that by looking at the historical data of these wells, like if in the historical data, if there's enough historical data, you should be able to see, oh, I changed injection historically in this particular injector, there was a change in injection rate. And after some time, I saw an impact on production of the nearby wells, because that should be evident in the historical data. And the model is trying to capture that behavior, that relationship between these wells through this machine learning algorithms. Internally, what it is trying to understand is that is there, like you are saying, okay, maybe there is a high permeability streak between these two wells. And if that is the case, the model is going to try and identify, it has to make the permeability high between those two wells in order to capture the fact that there is water channeling, because the historical data says so. So what we are trying to do is understand, inverse model that geological relationship by looking at the historical data and trying to match it. That's the idea here anyway. I mean, and again, these things will not work very well if you have 10 wells in the offshore field, because there's not enough data to build this kind of models. But the whole idea is that it is a predictive model. So it is a model, it's for mature fields where there's a lot of wells, a lot of historical data. So you can learn the relationship between these wells through the historical data. Does that kind of answer? Yeah, again, as I said, this is not a cure-all for everything. This is designed for a particular kind of problem where there is enough data that you can learn the behavior of the system from the data itself. Right? And that's not always true, as I said, and it might not be true for other kinds of problems for the same field. So anyway, so that was field level predictions, right? So now going to the well, so the idea is, of course, we're going to make changes at the well level. We're going to make injection rate changes at the well level. So of course, the models have to predict at the well level as well. So what I'm showing you here is a scatter plot of the cumulative production of each producer for that 5 years of that blue period that you saw. So each dot is basically a well in this case, or the cumulative, representing the cumulative production over that 5 years. On the y-axis, I have the true cumulative production for each well. On the x-axis, I have the mean of the ensemble, the predicted value, right? So this green line basically is where if I had a perfect model where I predicted every well perfectly, all these dots will fall on that green line, right? So basically, it's basically a scatter plot, right? So all these dots will fall on the green line if I had a perfect model. But of course, we could never have that because, as I said, I mean, the models are approximate, the data is noisy, and there are assumptions in the modeling and the physics and all of that. So you'll, of course, never have that. But ideally, you want these dots to be close to the green line, right? And you can represent that through statistical measures like Pearson correlation or rank correlation, and all kinds of statistical measures are there. So if, for example, if the rank correlation or the Pearson correlation is 1, then all these dots will fall on the green line. If it is 0, then it will be scattered throughout. So it's kind of a simple metric to tell you how dispersed these dots are, right? And so way to quickly understand this is a good model or not. So what we have seen that from working at various, working now over many fields, correlations of about like 0.6 is usually good enough to get a result. That doesn't mean it's again, it's not a perfect model to optimize. The whole idea here is, if you remember, fit for purpose. We want to do better than what the status quo is, right? And the status quo is, it's not generally very difficult to do better than the status quo when you have complex fields where there are lots of us, because those are for sure not optimized. They are not, nobody's operating them optimally. So there's always room for improvement. So we're not looking for the global optimum. We're just looking for a better solution than what's happening today. And that's usually good enough. So that's I mean, that's one way to understand, again, like it's a good model or not. Then, oh, sorry, I forgot that I have this. Okay. So then there are other ways to look at it. I remember I said that our models have the physical equations in them, right? So now going back a little bit, maybe to the geology question. So models do have properties like permeability, porosity, all those properties are there. But what we are saying that we initialize the models initially with some random, theoretically random realizations of permeability or random ranges. In this case, this red histogram is a prior distribution of permeability, right? It goes all the way from like 1 millidarcy to 3,000 millidarcy. It's very wide range. But what happened, the blue histogram is the converged distribution. So after you've trained the model to the historical data, all the models converge to this about 1,800 millidarcy, right? So now this is another way to validate the model. So you can go back to the geologist or the petrophysicist and say, hey, I gave it a very big range of permeability, but it converged to 1,800 millidarcy. Is this realistic for your field or not? If it is not, then there could be two things. And problems, so for sure it can converge to wrong values as well, or our understanding of the reservoir is wrong, and therefore, I mean, either way you have to go and reconcile it and figure out something is wrong. I need to sort of understand that, right? So that's one way to look at this. You can also look at reservoir pressure predictions, etc. You can look at things like connectivity. What this is showing you is basically the relationship between injectors and producers. So you can get these kind of things out of these models by running the models in perturbation mode and things like that. So this is as reservoir, okay, that makes sense. Does these connections, I mean, this is, for example, that this it's a very strong connection. It could, because there is a channel between them. So these kind of things, you'll go back and then talk to the geologist. This is saying there is a strong connection in between this. Does the geology support it? And you, as a geologist, you might say, yeah, it does or it doesn't. If it doesn't, then maybe it's wrong. Then you go back and look at the data, understand something is wrong or not. So various ways to kind of validate these kind of models, right? So anyway, so that's that. So once you have validated the models, then you go to the optimization problem, right? So what in this particular, the operator was interested in two objectives. One was injection capacity, other is at present value over 15. Blue triangle is that do nothing or the base case, basically injecting as is, not changing injection rates from what it is today. And this is the Pareto front, right? So these are all the optimal scenarios. And in this case, in the control variables are the injection rates of all those mandrels that I talked about. So what you'll see here, the operator decided to go with this plan, this red square. That is an operational plan that is supposed to increase net present value by about 8%, while injecting almost the same amount of total water. You can see about 65 or 68,000 barrels, but about 8% increase in net present value, right? So one good thing about these kind of optimization problems is it's not a capital intensive problem, because you are not actually drilling new wells. You're just going and changing injection rates in existing wells, which is only an operational expense. But the increase in net present value is quite significant, right? So this was quite exciting to them, and they wanted to go and apply this in the field. But as you guys know, whoever has worked in the oil fields, you'll know that it's very difficult to go and implement something exactly. Okay, a model is saying I want to do this, but then when you go in the field, there are other constraints, there are operational things happening, so it's very difficult to exactly do something. So the operator ended up in about implementing about 85% of the plan, of the optimal plan. And what we did was we took that actual implemented rates and then ran the model again with the actual implemented rates. And that is expected to give about 5% increase in net present value. So it's not, this actual plan that they implemented is not on the Pareto front, but it is still better than the base case. So, I mean, it's good enough. 5% increase in production with very little capital cost. It was good enough for them. So this is what they were interested in. But now the question is, this is still a prediction, right? This is in the beginning of 2019. So this is when we started the implementation. So this is still a prediction. This is not reality. So the question is, how well did the models actually do, right? So the next slide shows you that. Okay, no, actually, next slide is actually what they did. So, okay, yeah. So this is actually what they did. What changes did they make, right? So if you remember, I said it is a field with mandrels injection. There are a lot of layers, but they have only about 10, in this case, about 10 to 12 mandrels. So what we did, again, working with the petrophysicists and the geologists, to group those 80 layers into like 8 operational zones or units, basically. And the idea would be that we're going to change injection rates for this operational whatever major layers you would want to call them, major geological layers. And each of this is one of those major geological layers, and they can be related to the mandrels, basically, of the injectors. And each of these dot is one of those injector mandrels, basically. So the green dots are the dots where the model is saying that I need to increase injection compared to the base case, and the the red dots are the injectors where the model is saying I need to cut injection compared to the base case, right? So you can see that this is a very complex operational changes, right? It's not something trivial that some engineer can sit around and then figure it out on their or by themselves, because there's too many changes here, right? But you can see some higher level ideas, right? You'll see, for example, there's a lot of green here compared to red for this particular layer. Same as this layer IG has a lot more green than red. And in other layers like this, there's a lot more red than green. So what's basically happening is that the optimization is saying I need to move water from these layers to these layers. If you remember in the last slide, I'm keeping the total injection almost the same, about 65,000 barrels, right? So then I have to move water from some layers and put in some other layers and wells. So that's what's happening here. So what's happening is that you're moving water from these layers to these layers. Of course, and you're also redistributing the water horizontally between the wells. So it's both a vertical and a horizontal redistribution of the water. That's what's happening, right? And again, it's quite complex to understand, but once you start looking at this and kind of see these higher level patterns, then as engineers, you'll say, okay, does it make sense? Does it not make sense? In this case, the engineers agreed that it did make sense that to move water to these layers, and because they also felt that there's more unswept oil left in these layers, and that's what they decided to do. So then this is exactly what happened in real life. So this is daily oil production for that unit, the fault block that we are modeling. And what you'll see, this is daily oil production. This is the start of the project, right? This is where we started the project. And as I said, if you remember, they wanted to treat this as a controlled experiment, because otherwise it's very hard to understand. Because if you're doing many changes, the impact of the changes you did because of this injection could be difficult to understand. If you're also drilling new wells and also doing these things, what came from the new wells and what came from the injection changes, very hard. They decided to stop everything, like all workers, all new injection, and all new drilling, and only make these changes based on the model, because potentially the price is very big. If it works here, they can take it and to the entire field, and then that can become a very big deal for them. So that's why they wanted to treat this as a controlled experiment. So this is where they stopped all drilling, and you can clearly see there's a very nice exponential decline, right? So this is a log scale, so it's a very nice exponential decline going on. This is where the injection changes were made, and you can immediately see that within a matter of like few weeks, production completely flattened out, right? So this is that basically the injection effects starting to occur. And this is a very low compressibility water flood with very close, the well distance being very small. So the impact was very, very soon, almost like in 2 weeks, we could see the impact of changes. It starts declining again after a few months. And this happened actually because of some operational change issues. Some of the injectors went down because of some, I think, storm or something, if I remember. But then once those injectors came back up, it still remains flat, as you can see. And then at this point, after a year, we did another optimization. Again, the closed loop, if you remember. So we updated the models, we re-optimized, and we made the changes, and production kept stable. And then we have done another optimization here actually, and it's still stable. So this, if you project forward the base case decline, the difference between that base case decline and the actual production was about 15%. So this is agreed upon by the operator, and this was published together with them. So this is kind of showing like, okay, this actually worked in this particular case. The results actually made sense, and it did work well. So that's kind of the high level picture here. Any questions so far? Okay. So how are we doing with respect to time?
Probably wrap it up.
So then I guess, I mean, I don't need to go to the other example. I mean, it's kind of the same problem. I mean, the problem is optimization problem is different, but the idea is the same. Like multi-objective optimization using these kind of models, right? So, I mean, if you guys, I mean, it's up to you guys. Do you want to see the other example, or you guys are okay with what you saw and you have a general understanding of what basically I'm trying to say? I mean, up to you guys. In this case, yes, maybe as a cell, let's quickly do that then. Yeah, so in this case, it's the same kind of problem. So basically, a lot of historical wells are already there. In this case, about 225 producers, injectors, 311 producers, water flood again, same kind of model is done. So we did the same kind of modeling, build the back test. Okay, it's a good model, realize all of that. Now the optimization problem is where things change. Instead of optimizing injection rates, what we optimize is the location of the injectors, location of the producers, new producers to be drilled, and also trying to identify what is the optimal number of producers to drill. And the way you do that is, again, the Pareto fund now is different. So in the Pareto fund, you have number of wells on the y-axis, and the NPV on the x-axis is still the same, right? You want to maximize NPV. So the interesting thing about the Pareto fund here is a discrete Pareto fund, because well count is a discrete variable. You cannot have 2.5 wells, right? So you'll see the Pareto fund is like this, right? There are no points in between because you cannot just have half wells, right? So the interesting thing here you'll see is this. So each green dot is basically a Pareto optimal location, right? So if you drill one well, this green dot represents the best location, the optimal location of the well. These purple dots, these are all dots, actually, it's hard to see them, are non-optimal location of that one well, right? So the best well is that whatever this is located is going to give you the maximum net present value. So this green dot is the optimal location if you have to drill 2 wells, right? And so forth, right? So you'll see basically that as you drill more wells, of course, the Pareto fund keeps going up, right? You drill more and more wells, you're getting more and more net present value. But at some point, you see the Pareto fund flattens out. Basically, what that basically means is that for example, this flattens out at about 11 wells, right? So the 12th well that you're going to drill, even the optimal location of the 12th well is not going to give you enough incremental production to justify the cost of drilling. So that's why the Pareto fund basically becomes flat. And after some point, it will start going down. So what this basically means is the optimal number of wells to drill in this case is about 11. Right? So that's how you identify the optimal number of wells. So now, with respect to specific locations, in this case, these are the location. I think these are the 10 wells, 10 or 11 are very close. So you see this red dots are the optimal locations of those the wells that's going to maximize your production. In this case, about a 25% increase in production by drilling those 11 wells. And then 17% increase in net present value. So this was validated with their engineering, in the sense that this was very similar to their drilling plans that they already had, which was great. But the big benefit of this was, to do this, it took us about 4 hours. Once we had built the model, and in fact, the model was built for water flood optimization, but we took the model because the same model can use for other kinds of optimization problems. We took the model and just ran a different kind of optimization. It took us 4 hours to do this, but if you had to do an actual, like a properly, and if you have to try to find these optimal well locations, like in a traditional manner, it's going to be far more than four hours of work, right? And of course, this is, again, you cannot just rely on their model like this and say, great, I'm going to drill these wells now, right? You have to do your normal due diligence. You have to look at geology, you look at all other aspects as you traditionally well, but this will give you like a head start in a way, right? You can understand, okay, I need to look at this, does it make sense or not? You have to still do your normal due diligence, but it kind of gives you that additional like speed or additional another way to look at the same problem and hopefully understand this better, or feel better, right? So that's the general idea. Anyway, and that's, I think, all I had. So to summarize again, so the idea is that we're trying to combine reservoir physics and machine learning into this unified models. So try to bridge the gap between these two different worlds, right? One, that of traditional machine learning, simulation and modeling. The other is data science and machine learning. How do kind of bridge the gap between these to sort of come up with these models that are kind of have the best of both worlds. And again, the whole idea is speed in one sense, making the models fast, not only from the perspective of building them, updating them, running them, but also having long-term predictive capacity. And then you saw example applications to water floods, but we have applied this to steam floods, to hydraulic fracturing modeling, to allocation problems, all kinds of different problems. And finally, like any modeling approach, these also have limitations. As I said earlier, this is applicable to fields that have a lot of historical data, mature fields in general. It's not applicable to green fields. It's not applicable to offshore fields with 5, 10 wells, because there's not enough data to build this kind of models. So that's all. Thank you very much for listening.
Yeah, this is, it's for.
Yeah.
But geothermal, it's the same thing, fluid migrating on the ground.
Yeah.
Using energy directly to, you know. Is it easy to extend this approach?
Yeah, so the question is, can these kind of techniques be applied to other kinds of problems like geothermal, right? Theoretically, absolutely yes, because it depends. I mean, these techniques are not limited to the physics you're modeling. Depending upon the physics, if you change the physics, then the machine learning part is very general. Now, if you have the right physics, then you can solve the problem for that kind of problem. We have applied these to CO2 UR, for instance, like which is, again, it's a different kind of physics, not water flood. You have miscible gas injection, and we applied it successfully to your CO2 UR. We can also then extend it to CCS, which is carbon CO2 storage problems, which are different kind of problems. Now we have applied it to steam flows, which is energy, which is also requires thermal modeling. And geothermal is thermal simulation in some sense, right? It's single phase thermal simulation basically. So we have applied it to steam floods, so which is multi-phase thermal simulation. So in that aspect, I think it is directly transferable. I would presume, but we have not done that for. Yeah.
John?
Sure. Yeah. Yeah. Very good question. Yeah. So, so we started here in San Mateo, right? I mean, me and my co-founders are from Stanford. So the CEO, who is a very charming guy. I mean, he's no longer with us anyway. He moved on to run his own VC firm. So he was a Forbes 30 under 30 like a few years back. So anyway, so he was a bachelor's from physics, not from petroleum engineering, but then he kind of got excited about like data and applications of data to oil and gas when he talked to like many industries and figured out that oil and gas seems to be the most backward in terms of applications of data science and machine learning. So he thought, great problem to solve. So anyway, he was able to convince some VCs to give them money. So he raised $1 million as a first seed round. And one of our biggest investors is Founders Fund, Thiel's fund, I know who invested in Facebook and others. So overall, we have raised about $45 million so far, and we are about 50 employees now. And then, well, of course, I mean, when we started, oil was, I think when we started, oil was at like $60-$70 or something like that, and immediately after we started, oil, well, like in 3 months, oil went to like $30 or something. So not the best time to start. Yeah, not the best time to start a startup in oil and gas. So yeah, like I think first 6-7 years was indeed difficult for us because oil never rebounded for a long time, right? And then yeah, it was difficult time for the oil and gas industry. And then when oil is at that kind of price, people are not interested in like trying out new technology, unproven technology, right? But I think we still managed to stay along. And then since 2020, I think there was a change in management, change in like the product. We have done a lot of changes to the product, making it user friendly and all kinds of stuff. We also have a new product line I was talking to Paul about. So now this is one of our key main businesses, but we have got into the space of carbon management. So greenhouse gas modeling, end-to-end platform for greenhouse gas modeling, which is basically, I mean, nowadays with all the regulations coming, it has become important. Every company is looking for ways to sort of minimize their carbon intensity, right? And then how to forecast that forward. And so we have a platform that basically does that, which is doing quite well. So that's kind of the high level picture. So we're mostly remote company, but most of our employees are in Houston and in Colombia. So we have a like big office in Colombia, about 20 people are in Colombia, in Medellin, because the current CEO is Colombian, and there are a lot of other reasons. Of course, it's cheaper to hire there, and there's a lot of good talent there. It's Medellin is called the Silicon Valley of Latin America today. It's growing very well, and a lot of opportunity for good engineers to find and so forth. So all of that reasons, we have people in Houston and in Colombia mostly. And in terms of clients, we are kind of all over the world. We have a lot of clients in Latin America, as I said, Argentina, Colombia. We have clients in Middle East and clients in Asia, like India. We have Thailand and North America, quite a few now, especially in the carbon management side. We have quite a few clients in North America. Here, there are not a lot of water floods. Like most of it is all unconventional now. Now our main focus is secondary recovery processes. So most of our clients are international.
Thank
Thank you.
Follow you up, Georgia. Something for our guests.